Welcome all. Welcome to another mathematics and high energy physics seminar. We are delighted to have Professor Thomas Hartman with us, who is currently a full professor at Cornell University. After earning his PhD at Harvard University under the supervision of Professor Andrew Strominger, he went to Princeton and the UC Santa Barbara for postdoc before joining Cornell. His research largely relies on quantum gravity, AdS/CFT, and the related models, who speaking on emergence of space-time today. And during the seminar, just kindly remind you that if you have any question, please use the raise hand button on Zoom. I will then grant you speaking permission. And your active participation is very, very appreciated. And now I will pass the conference to Professor Thomas Hartman, and thank you for accepting our invitation.
Okay, thanks for having me. So I want to first reiterate what Jesse said about questions. I'm very happy to have questions and discussion during, and we can. That's fine. We can have plenty of back and forth. That would be great. So please do jump in with questions, and we can go off on tangents and discuss whatever comes up. The topic, the emergence of space-time, is a big one, and I decided in this lecture to focus on one aspect of this, which is the recent progress that people have made on understanding black holes and quantum gravity. And in particular, I want to talk about some both old and new results on gravitational path integrals, because a lot of this recent progress has been coming from understanding gravitational path integrals better. And so my outline is I'm going to do this lecture in two parts. So in the first part will be sort of a Blackboard style lecture on black holes from the gravitational path integral and the basics. This, I think, will be partly review from the lectures that you had, but I thought it would be good to go through it from another point of view and understand how the black hole geometry, especially how the Euclidean black hole, comes about from the gravitational path integral. And then in part two, I'm going to go to more of a seminar style and jump to slides and describe the recent developments surrounding space-time wormholes and how they're used to understand the entropy of Hawking radiation. I have here a few references that I'll just flash up for a second. And I guess the recording will be posted, so if you want to look at that later, you can see these references. So I want to start with some discussion of Euclidean path integrals. In ordinary quantum field theory, so at this point, we're talking about path integrals without gravity. We're going to come back and add gravity after getting through the quantum field theory discussion. The starting point for path integrals is that they calculate transition amplitudes. So if you have some state phi of x, say it's a state in a field basis, so we'll call that phi1 of x, then you can evolve it in Euclidean time by acting with e to the minus tau times the Hamiltonian. And then you can calculate a transition amplitude to another state, phi2 of x. And the basic statement of the path integral is that this is integral d phi of e to the minus action. In this case, we're in Euclidean signature, so this is the Euclidean action where the boundary conditions on the path integral are given by these field values phi1 and phi2. It gets tedious to keep writing this integral over and over again, so I'm going to represent expressions like this with a picture. The picture that I'll draw is this. Okay, so this picture has a phi1 at the bottom where we impose the field data phi2 at the top, where we impose the field data again, and it's a slab of Euclidean spacetime of length tau. Okay, so this picture on the bottom, this picture here is just shorthand for doing this path integral, and I've written the boundary conditions as the data that specifies how we're supposed to do that path integral. And then we integrate over all the field configurations on this manifold that I've drawn. Now that I think is familiar. A formal thing that we can do with path integrals is that we can cut them open. And when we cut open a path integral, the cut path integral defines a quantum state. So what I mean by that is the following. So let's take, for example, the state psi, which is e to the minus tau h times a field state phi1 of x. So how do we construct this quantum state by a path integral? Well, we start by putting the field data, then we evolve it in Euclidean time by an amount tau, and then we leave here an open cut, which I'll represent with a squiggly line. And that just means that I have not specified the boundary conditions on that tau, on that slice, on this slice here. So if we haven't specified the boundary conditions, this is not a number, it's a formal expression, which you can think of as a linear operator on fields. So in other words, we take this quantum state, then given a quantum state, we can calculate the wave function of that state. The wave function of a quantum state, psi of phi of x, we're in quantum field theory, so wave function is wave functional as a function of the quantum fields. The wave function is by definition the overlap of the state with the field state phi, and then that wave function is given by taking this cut path integral and inserting in the cut path integral, inserting the field data phi2 as a boundary condition on the open cut. Is this clear? Are there questions? Is this well known to people? Or maybe they don't have mics, but if there are questions, raise your hand or stop me here. So another example of a state that we can make is the ground state. So the ground state can be prepared by a path integral. The way to prepare the ground state is to think of the ground state as being what you get if you take any state and then you evolve it by e to the minus tau h, and you send tau to infinity, because that'll just project you onto the lowest energy state that appears. So you started with some superposition of energy eigenstates, and all but the ground state will get projected out by this operation of evolving in time. And that means that when we represent this as a path integral, we can write it like this, where now we do the path integral on a half space. That is, we do the path integral over half of Euclidean time. So this is now infinite, and then this open cut at the top represents some unspecified data that we have to impose, and then we could calculate the ground state wave function by putting some data on that slice. So that's how we think about quantum states as prepared by the path integral. Similarly, a path integral with two open cuts defines an operator. So, for example, if I just do this path integral on a piece of space, on a piece of Euclidean space of size tau, and I don't give you boundary conditions on either top or bottom. So if I leave two open cuts, both at the top and bottom of the strip, then this is equal to the operator e to the minus tau h. And if I want to calculate the matrix elements of that operator between two states, then I need to supply boundary conditions for the two states on the top and bottom cut. So let's apply this to reproduce something that maybe you're familiar with, the thermal partition function. So the thermal partition function in a quantum, in a general z of beta in a quantum system is the trace of e to the minus beta h. Now, this e to the minus beta h, well, that's exactly the operator that we were just talking about from the path integral. So this is the trace of an operator that we can write using the path integral as this integral on a strip of size beta. Now, what does it mean to do that trace? Well, it means that we need to, to do the trace, we can do the trace in the field basis. So let's do an integral over fields, integral d phi of x of phi of x e to the minus beta h phi of x. In terms of the path integral, this means that we do an integral over all possible field data phi of x and then we do the path integral where you put the boundary condition phi of x on the bottom of the strip and you put the boundary condition phi of x on the top of the strip. And for thermal case, you take the strip to be size beta, where beta is the inverse temperature. Now, when we do this path integral on the strip, what are we doing here? We're doing a path integral on the strip with the same data phi of x at the top of the strip and the bottom of the strip. So we have the same data on the top and bottom, and then we're summing over it. Well, that's exactly the same as just gluing the two ends of the strip together. So just identifying the fields at the top and bottom. And therefore, we can do the integral. The integral pastes the top and bottom together and glues the strip into a cylinder of now circumference beta. So the conclusion is that z of beta is equal to this diagram where, again, this diagram means that you should do the path integral over all field configurations on the diagram on the Euclidean space-time that's drawn here. Was there a question?
Yes,
yes,
thank you. Hello, Professor Hartman. What about if the theory has some non-diagonal matrix element?
Here I was specifically talking about in
Diagonal.
I was only in flat space right now. So this is only in flat space. The general, in general, if you have a QFT on some space sigma, then the thermal partition function z of beta would be the path integral on sigma times S1 beta. So you can always get the thermal partition function on some space sigma by multiplying that with the Euclidean time circle with the size of the circle set by the inverse temperature. Does that answer your question?
I mean, in the previous page, maybe in this page up, there's like this one in the middle, you have this metric element, bra phi e minus beta h cat phi. So, but there's some theory where you have.
Oh, I see. Sorry,
yeah.
I see. I misinterpreted the question. Okay,
Yeah.
You're asking about the off-diagonal terms.
Exactly.
So those do not contribute to the thermal partition function. They exist. They are non-zero, but they do not contribute to the thermal partition function because the thermal partition function is defined to be a trace. It's like when you take the trace of a matrix, only the stuff on the diagonal, the trace is just the sum of the stuff on the diagonal. And the same is true of this operator. It's only the diagonal contributions to the operator that contribute to the thermal partition function.
I mean, I'm asking because, for example, if I take a C52, let's say, and I have the Virasora symmetry, and then I have this Virasora stay and descendants, but the matrix element of descendant and stay have some non-diagonal, non-zero matrix element, and they contribute to the partition function. That's
the off-diagonal terms. The off-diagonal terms do not contribute.
For example, I can have L minus 2, this Virasora operator acting on some asymptotic state, and in the right I can have L minus 1 squared. I think that this is, I mean, by non-diagonal. L minus 1 squared. It does.
Yeah, it exists, but it does not contribute to the thermal partition function.
Okay.
Just because it's a trace. Are there other questions?
Okay.
So another nice application that we can get from this way of thinking about things is that it's very easy to understand Hawking radiation and Unruh radiation. So let's do the case of Unruh radiation. So Unruh radiation is the radiation that you have when you're restricted to a half space. Okay, so if this is a picture of Minkowski space with time going vertically, then the wedge on the right is called Rindler space, and an accelerating observer in Rindler space will detect a temperature. This is almost the same as the effect of Hawking radiation, but it's a little easier to think about because you can see it already in Minkowski space. So what I'm going to describe now is how we can understand Unruh radiation from the quantum field theory path integral. So we'll start by writing down the state. So the state is vacuum, which we'll call 0. And therefore, the density matrix is 0, 0. Okay, so this is just the vacuum density matrix. And if we write this as a path integral, we have rho is equal to, remember that we can prepare the vacuum by doing a path integral on a half space. So this is Euclidean time tau less than 0. And this part up here is Euclidean time tau greater than 0. Since rho is an operator, we have two open cuts here where you need to supply boundary conditions in order to turn this operator into a number. So far, all I've done is I've written two copies of this path integral on a half space. But now what we're going to do is we're going to separate the space, we're going to separate space into two regions. So we're going to separate space into a region A plus region B, where those are the two half spaces. So on my diagram up here, we have A is on the left and B, actually, let's do it the other way around. Let's put B on the left and A on the right. And when we do that, it's approximately true that the Hilbert space, there's a caveat here, which I'll come back to, but it's almost true that the Hilbert space of the theory splits into two parts and is a direct product of the Hilbert space on A times the Hilbert space on B. This is not quite true because of UV divergences in quantum field theory, but for our purposes, it's good. It's close enough to being true, and those UV divergences can be regulated. Now, in terms of the path integral, so in terms of the path integral, we have the state is originally on the full space, and that's the one we were writing here. But now what I want to do is define the reduced state on region A, which is Rindler space. So the reduced state on region A means we define a state rho sub A, which is the trace over everything on region B of the original state rho. So let's write that as a path integral. We want to do a trace over B, and then rho was two copies of the vacuum state, which I'll draw this way. And here we have B on the left and A on the right. Now, when we do the trace over B, so let's think back to what happens when we do a trace. When we did the trace to get the thermal state, what did we do? We imposed a boundary condition on the fields. We imposed the same boundary condition on the two cuts. Then we sum over it. And that had the effect on the manifold of gluing the two pieces of the manifold together. So remember when we did that a few minutes ago for the thermal case, we were doing a trace of this strip, and that had the effect of gluing the top to the bottom and giving us a cylinder. Now we're doing a trace on a different manifold, and it's going to have the same effect, though, which is to glue together the regions B here. So we impose field data on region B, and then we sum over it, and that glues the two regions together. Therefore, the density matrix on region A is given by this path integral. which is now on all of Euclidean space Rd. So this is a path integral representation of the density matrix rho A. And again, what all these pictures mean is they tell you that once you supply some field data, they tell you how to calculate a matrix element. So in this case, what it's telling you is that the matrix elements for some field data phi A of x prime, rho A, phi A of x is given by a path integral on this funny manifold with a cut where you impose phi A prime on the top of the cut and phi A on the bottom of the cut. So this formula here, this is just a number, because now you're actually doing the integral with some specified boundary conditions, whereas this formula here is an abstract representation of an operator, because that's a path integral where it's an integral where you have not specified the boundary conditions yet. It's a linear functional on its boundary conditions. Now that we have that formula, we can understand the Unruh effect as follows. So let's write it again. Rho A is this path integral. And now what we're going to do is we're going to reinterpret this path integral as a operator. To do this, I'm going to choose a slicing of this path integral, which is in polar coordinates. So I want to think in operator language, I want to think about starting with a state here, and then evolving that state around in polar coordinates. So we're evolving it around this way, all the way around until we get to here. In terms of this polar evolution, so let's give the polar angle a name. Let's call that theta. So what we're doing is we're evolving from theta equals 0 to theta equals 2 pi. And we know what the operator is that evolves you in the theta direction. It's the theta translation generator. So what we learn is that rho A is e to the minus 2 pi times k theta, where k theta is the rotation generator in Euclidean signature. This is very similar to the formula we had a few minutes ago. Let's go up and find it. This formula here. So here we have a path integral with two open cuts, and we said that this is given by the translation operator in time, which is the Hamiltonian, exponentiated as e to the minus tau h. We've done exactly the same thing to this path integral, but now it's the rotation generator that's being exponentiated, and it's going around by an angle 2 pi, so we have always inverse temperature 2 pi. But this is simply the thermal state with respect to k theta. This might sound a little strange, but this is actually a very natural thing in Lorentzian signature. So these path integrals are all being done in Euclidean signature. But when we go back to Lorentzian signature, the Wick rotation that takes us from the Euclidean plane to Minkowski space is theta goes to IT, where t is, well, let me give that a different name. Theta is I eta, where eta is the Rindler time. It's the coordinate that measures time in Rindler space and is the same as the proper time of a uniformly accelerating observer. The conclusion then is that the Minkowski vacuum rho equals 0, 0 gives you a reduced state rho A, this state in Rindler space, which is, first of all, it's mixed. We had a full state which was pure, but the reduced state is mixed. And secondly, is thermal. It looks like an ordinary finite temperature state for somebody whose proper time is eta, which is exactly the uniformly accelerating observer. Are there any questions? If there are no questions, I'm going to now continue and turn to the problem of doing path integrals with gravity. So far, we've been talking about doing path integrals in quantum field theory, and now we'll do gravity. Now, roughly speaking, a path integral in quantum gravity means that we need to integrate over both metric and field of e to the minus action of g and phi. But this isn't really exactly true. So I'll put this in quotes. This is a way of thinking about certain observables, but we can't actually do this path integral. Quantum gravity, of course, is not renormalizable. New degrees of freedom almost certainly need to be added in the ultraviolet, like string theory, strings and D-branes. But for the purpose of certain calculations, we can treat this path integral as an approximation to the low energy theory. And that's what I'll be doing anytime I refer to the gravitational path integral. What I want to do is to write down the path integral expression in quantum gravity for the thermal partition function z of beta. Now, in QFT, we derived a few minutes ago the formula z of beta is equal to the path integral on a cylinder of size beta. Now we would like to do something similar in gravity. But we have a problem immediately in trying to carry over this idea to gravity, because in gravity, we don't get to pick the manifold. So in gravity, we don't pick the manifold to do the path integral on. That's part of the path integral, right? When we do the path integral, we need to integrate over metrics. So it doesn't make any sense to specify the manifold of integration when we do a gravitational path integral. What we do instead in gravity is we don't specify the manifold. We only specify the boundary conditions on the manifold very far away from whatever matter fields we're interested in or whatever excitations we're interested in. So we only specify the metric at infinity, the boundary conditions on the metric near infinity. And then we do the path integral over all metrics satisfying those boundary conditions. Now, we believe it's true, and there's a lot of evidence for the proposal that the thermal partition function, z of beta, in quantum gravity is given by a path integral where the boundary condition is a cylinder of size beta. So what I mean by this picture is that it's similar to the pictures I had in quantum field theory, where we integrate over all the fields on a given manifold. But now we're not allowed to specify the manifold because we're integrating over the metric. So what I mean by this picture is we integrate over all possible manifolds and all possible fields on those manifold, on that manifold that specify the boundary condition that I've written here. In other words, that the metric near infinity is approximately d tau squared plus dx squared with tau identified tau plus beta. Let me pause for questions. Any questions?
Maybe I have a question. If it's an S1, why isn't something like R squared d tau squared plus dx squared? Sorry, maybe like the length square, the x squared d tau squared plus dx squared, things like that.
Because let's see, tau is time. So like very far, very out near infinity, it should just be flat space. What I've written here is just Euclidean flat space, except that I've wrapped up the time coordinate tau. So there's no other factors. There's no other factors in there.
Yes, but topologically it looks like it's like S1, but if the metric is as flat, then the Euler character should be 0, but S1 does not have 0 Euler character.
Well,
something very common.
The Euler character, in order to calculate the Euler character, you have to fill in what happens over here. Right? So far, we've only said the boundary conditions. And you're right that there will be a factor like that when we go deep inside, there will be a factor like that. But this is certainly a flat metric, right? It's a flat metric, and right. I'm assuming that we're in asymptotically flat space, so this is the right boundary condition. If we were in asymptotic ADS, then there would be some factors in order to satisfy the asymptotic, in order to satisfy the asymptotic equations in ADS.
Okay, thanks for answering my question. And another participant has a question.
Yes. Could you expand a little bit why there is such a postulate? Is it related to the fact that, or not fact, the idea that at infinity it's kind of vacuum, something like that? I mean, the question is like maybe why there is this postulate.
Yeah, I'll give two answers.
The arguments.
Yeah.
The argument.
Yeah. So one answer to that is that it's just the closest thing we can do to what we did in quantum field theory. We're not allowed to specify the cylinder everywhere. We are allowed to specify it at infinity, so it's the closest thing we can do. That's not a great argument, but that's the starting point. And then over many years, people have applied this postulate and shown that it gives reasonable results. So for example, if you take this postulate and you use it to calculate the partition function, and then you calculate from that, let's say the energy. You can take a derivative and get the energy. Then it correctly gives the energy of the black hole, which is its mass. Or if you take this formula and you calculate from this the entropy, you can do 1 minus beta d beta log z, which is a standard thermodynamic formula to calculate the entropy. And that gives the Bekenstein-Hawking entropy area over 4, which matches with all the other results that we have in thermodynamics. So it does seem to be giving a reasonable partition function. Now, that's all the evidence that existed before ADS-CFT. But now the evidence is even much stronger than this, because in ADS-CFT, which is one of the few fully non-perturbative, well-defined formulations of quantum gravity that we have, this postulate is a part of ADS-CFT. So ADS-CFT implies this postulate as a special case. In fact, you could sort of think of ADS-CFT as generalizing this postulate to all possible things you can do near infinity, as opposed to just putting it in a thermal state. So there's lots of evidence, both from these low energy sort of calculations, like thermodynamic calculations, and from more microscopic calculations in string theory that use the ADS-CFT correspondence.
Thank you very much.
So given this postulate, now we want to do the calculation. Like I said, we can't actually fully do the gravitational path integral. It's not even a well-defined integral. But what we can do is we can try to calculate the integral by the semi-classical approximation. In the semi-classical approximation, an integral like integral dg d phi e to the minus IE of g phi is approximated by summing over saddle points, that is solutions, summing over solutions of the equations of the equations of motion, the classical equations of the theory, of e to the minus IE of g bar phi bar, which denote the fields for that solution. This is the leading order semi-classical approximation. It's essentially the WKB approximation, where the action is large. And then there are corrections to that, which I'll just write as I1, I2, ... The first term here is the classical, this first term here is the classical solution. Well, it's the action evaluated on the classical solution, which is order 1 over g Newton. G Newton is Newton's constant. The other corrections are loop corrections, which come in at g Newton to the 0, g Newton to the 1, etc. So those are subleading corrections in the semi-classical approximation. So therefore, we can approximate the path integral as, well, let's suppose that only the metric is important. So I'm going to suppose that we can set the other fields to 0, which is often true in black hole situations. Then that means that we can approximate the thermal partition function in quantum gravity, z of beta, as e to the minus the Euclidean action on some metric g bar times quantum corrections in that background, where the z quantum term, so where this is the classical action and this is the quantum corrections. By the postulate, this g bar is a metric, which is a solution of the Einstein equations with boundary condition ds squared goes to d tau squared plus dx squared, with tau being a circle beta. In other words, we need to take this boundary condition that we wrote earlier, and in order to do the semi-classical approximation, the path integral in the semi-classical approximation, we need to find a solution. We need to remember we said this was just the boundary condition. We didn't get to say how we fill it in. It's up to the equations of Einstein gravity to fill in that manifold. But in the saddle point approximation, it gets filled in by a solution. So we fill it in by finding a solution, and the solution looks like this. This, I think, is something that you've seen in these lectures, but let me review it. So this is the Euclidean black hole solution. For example, if we're in 4 dimensions and we're talking about Schwarzschild black holes, then the metric is ds squared is 1 minus 2m over r d tau squared plus dr squared over 1 minus 2m over r plus r squared d omega squared on the sphere, where tau is identified tau plus beta, and beta is the inverse Hawking temperature, 8 pi m. In this picture, tau is the direction that goes around the circle because that's the one that's wrapped up. R is this direction. So this point at the tip here is the horizon, the Euclidean horizon, r equals 2m. And then r is the direction along the cylinder. Notice a big difference from what we found in quantum field theory. In quantum field theory, so let's sort of recap the difference here. In QFT, we said z of beta was the path integral on a cylinder. Of size beta, whereas in quantum gravity, z of beta is a path integral with an asymptotic cylinder of size beta. But we need to solve the Einstein equations, and the Einstein equations have a solution that caps off at the horizon, r equals 2m. So using this Euclidean solution, you can now do the calculation of the action. So you take the solution, you plug it into the Einstein action and calculate everything, and you can find the free energy or the partition function z of beta for the black hole. Are there any questions? We need one last thing for part 1 of this lecture, and that is to understand the state of a subregion, which I'll call R, outside the black hole. Really, actually, not just outside, but far away from the black hole. Now, just like when we talked about Unruh radiation, so in the Unruh effect, we had a space which was just flat, and then we calculated the density matrix of a region by putting in this funny cut in our flat space, and it was the path integral on that with that funny cut that defined the density matrix on Rindler space. We're going to do something similar now for the black hole. So rho sub r is defined by doing the path integral on this Euclidean black hole, where we put in one of these funny cuts far away from the black hole. So this region here is region R. And this path integral represents the semi-classical calculation of the density matrix rho sub r. I've cheated a little bit here by drawing the whole manifold. To be more careful, what I should say is that rho sub r is defined by doing the path integral with these boundary conditions. Put some dots here. So this density matrix is an operator in quantum gravity defined by doing the path integral with these boundary conditions. But we know that in the semi-classical approximation, it's going to end up being filled in by a solution of the Einstein equations, and that solution will be the Euclidean black hole. This formula is, so remember this formula, because I'm now going to completely change gears, but we're going to come back to this formula and we're going to use it in the calculation that I'll do in part 2. Let's stop here and take like a 3-minute break and see if there are questions, and I'm going to switch to slides on my. Okay, we're back with part 2. So in part 2, we're going to discuss recent progress on understanding Hawking radiation from the gravitational path integral. And this will be a discussion of space-time wormholes and the page curve and the black hole information paradox. So I'm going to start with some motivation. So these are slides that I patched together from old talks that I've given about this. This will be now more at the level of the kinds of things that people have been thinking about the last few years, and will tie together to this general discussion path integral. So black hole thermodynamics, as you know, black holes produce Hawking radiation. Produce Hawking radiation at the Hawking temperature. And what was understood in the 70s is that it's not just the temperature. They actually, everything you do to a black hole, it responds as if it's a thermodynamic system. This is very strange because black holes in classical gravity don't have any moving parts. They're not made of anything like a star. They just appear to be pure space-time curvature. So it's a big puzzle in the quantum, it's a big puzzle in understanding gravity to understand why they seem to obey the laws of thermodynamics. And they obey these laws with a formula for the entropy, which is 1/4 the area of the black hole horizon. This is measured in Planck units, so it's an enormous number for an astrophysical black hole. Like Sagittarius A star is the black hole that we have at the center of our galaxy, the Milky Way. The entropy is 2 to the 88. So this is some huge number of degrees of freedom that the black hole should have. Because in a quantum theory, S should be the log of the number of states. And so a big question in quantum gravity is understanding where those states, or how to understand, is trying to understand what those states could be. There have to be some big number of states. In other words, a black hole needs to be made of something with lots of moving parts. And we have not really identified how to make sense of those parts. The working hypothesis, not the only possibility, but I think the one that I find most plausible is that black holes are unitary quantum systems. We don't need anything dramatically new, like a violation of unitarity, but that a black hole is an ordinary unitary quantum system with the number of degrees of freedom given by its area. This is what the thermodynamics of black holes very strongly suggests. Now, as I said, these degrees of freedom are not visible in the classical theory, but if this hypothesis is true, then they must exist in quantum gravity. So one of the ways of posing the problem of quantum gravity is to find these states. Now, this sounds like just a question about black holes, but it's actually a much bigger question than that, because remember that black holes are just pure space-time curvature. They're just made of the metric. They're not made of anything else. And that means that in order for there to be some hidden degrees of freedom here, space-time must be made of something. So if black holes are ordinary quantum mechanical systems, then space-time itself is made of some parts. It's emergent from the collective dynamics of these quantum parts. We don't understand what those are, but it seems very likely, based on black hole thermodynamics, that space-time actually needs to be made of something in quantum gravity. So the consequences of this unitary hypothesis are very large. There's a lot of evidence for this idea that black holes are ordinary quantum systems, coming from black hole thermodynamics, coming from counting the states in string theory, coming from ADS-CFT, where we have a very precise mapping between quantum states and black holes. However, there's a problem with the unitary hypothesis, which is called the black hole information paradox. And this is an idea that Hawking first pointed out in the 70s, that when a black hole evaporates, it seems to violate the laws of ordinary unitary quantum mechanics. Because when a black hole evaporates, you start out, say, with a star in a pure state. Now you let the black hole evaporate. It evaporates by the Hawking process. When it evaporates, the Hawking calculation, or the density matrix of the Hawking radiation, is very much like this calculation we just did in part 1 of the Unruh radiation. So you get a thermal state for the Hawking radiation, and it's a mixed state. You get a thermal mixed state. But in ordinary unitary quantum mechanics, it's impossible for a pure state to evolve into a mixed state, and that's the problem. So it's hard to see, given the information problem, how black holes could really be these ordinary unitary quantum systems. Now, what I'm going to do in the rest of the time here is to talk about one particular piece of this information. The information problem is a big one that covers many areas of quantum gravity. I'm going to talk about one particular piece of it, which is understanding the entropy of the radiation. There was a question.
Yes. Why the state of a pure star be treated as a pure state?
Well, an actual star will not necessarily be in a pure state, but we can choose, if we can just consider that to be a state. We can consider a pure state. So we can choose a star to be in a pure state and study the evolution of that state.
I mean, in what sense pure state? Because I mean, I imagine stars, huge object, many particles, a lot of difficult things. So in what sense a pure state?
Well, pure state just means that there's a wave function describing that state. You can have a pure state can have many.
Mean that the entropy is zero? It's mean that the entropy of this is zero, of this star, or
yeah, it means that. It means that the von Neumann entropy is zero. So the von Neumann entropy is a fine-grained entropy. I'm going to talk about the von Neumann entropy a little bit later, but it's a fine-grained entropy, which is like an entropy when you know the exact state. And now, when you have a pure state and you know the exact state, there's no uncertainty left, and the fine-grained entropy is zero. Stars have a thermodynamic entropy because they can be hot. Like, okay, there's some large number of degrees of freedom that's very hot, so they have thermodynamic entropy. but they can still be in a pure state where they have no fine-grained entropy. The thermodynamic entropy is an entropy where you throw away a lot of information about the system. You keep track only of the energy, not all the fine-grained details. Other questions? So the part of this that I want to describe is the physics of the page curve. And let me first describe what this page curve is. So first, what are we going to be calculating? We're going to be calculating the entropy of Hawking radiation. Now, the diagram that I have here is a space-time diagram for an evaporating black hole. I can't seem to get my mouse on. Let me see if I can get this so my mouse will show up. So in the past, we have a star. Then this star, time is going vertically. So the star undergoes gravitational collapse. It forms a black hole. Then the horizon of the black hole is well, there's a singularity, which is the squiggle, and then the horizon is the line at 45 degrees. And Hawking radiation is shown in the picture as these blue squiggles. Now, when Hawking radiation occurs, one way to think about it is that it's a pair production process. That when you create Hawking radiation, what's really sort of happening is that you're creating some Hawking radiation outside the black hole, which is entangled with some Hawking radiation inside the black hole, labeled here as the interior partners. So these are being created together, and they're in some entangled state. But when we observe the Hawking radiation, we only see the outside particles. And since we only see half of this entangled state, it looks thermal. It looks like it's mixed. Now what we're going to do, yes, okay, so the point being that Hawking radiation is a process of entanglement production where the black hole interior gets entangled with the Hawking radiation. Now we're going to define a region R, or R for radiation, which is a region out near infinity, far away from the black hole, where we collect the radiation. This is the big red line on the curve, and you can see that the Hawking radiation is going to go up and land in region R. Now consider the fine-grained von Neumann entropy of this radiation. The von Neumann entropy is defined by this formula that I've written here. It's minus trace of rho log rho. And as we were just discussing, the von Neumann entropy is not quite the same as the usual thermodynamic entropy. The von Neumann entropy is a fine-grained entropy that is the uncertainty you can think of as uncertainty when you know the exact density matrix. If you're in a pure state, there's no uncertainty, and the fine-grained entropy is 0. If you're in a mixed state, then there's still some remaining uncertainty given the density matrix, and therefore, in something like a thermal state, the von Neumann entropy is non-zero. Now what we're going to do is look at the behavior of the entropy of the radiation as a function of time. Okay, so we're going to plot this fine-grained entropy S as a function of time t. First, I'm showing Hawking's calculation. So Hawking's calculation says that the entropy, or says rather that the radiation is in a thermal state. So what you see in this curve is that as the black hole evaporates, there's more and more radiation, and it's some hot thermal gas. Well, not very hot. The Hawking temperature is a low temperature, but it's a thermal gas. And so as the black hole evaporates, the radiation just increases and increases until eventually the black hole is gone. And that's when the curve flattens out. So that's the von Neumann entropy of the radiation according to Hawking's calculation. now we can also consider the entropy of the black hole according to the Bekenstein-Hawking area law that says the entropy of the black hole should be its area over 4. And the black hole information problem becomes a problem when these two lines cross. So when the red line goes above the green line, that's when we have a problem, because the radiation entropy is supposed to come from entanglement between the Hawking radiation and the inside of the black hole. But if the black hole only has a total amount of entropy A over 4, then that's the maximal entanglement that you can have with the black hole. So the total amount of entanglement, the total possible entanglement is the green line, whereas Hawking's calculation seems to show that you're entangled by an amount given by the red line. So when these two lines cross, that's when you have a problem, and there seems to be a contradiction with the ordinary. There's a contradiction between Hawking's calculation and this idea that black holes have entropy A over 4. So there was a calculation about 30 years ago or so by Page, where he argued that if black holes really are just ordinary quantum systems that behave unitarily, then the true entropy of the Hawking radiation should follow the dotted curve. That is, if black holes really are unitary in quantum gravity, then Hawking's calculation should be correct at early times. At early times, the radiation should increase so the entropy of the radiation should just go up because it looks thermal. But at some point, there should be a sharp transition where as more radiation keeps coming out of the black hole, the entropy starts to go down. The way Page did this calculation is by modeling the time evolution of the black hole as a random Hamiltonian. So this seems like sort of a drastic approximation, but we're going to find that using modern path integral techniques, you can confirm this calculation now. So Hawking, we need to be careful a little bit about exactly what we mean by a problem, because Hawking is working in the low energy effective theory. So when Hawking, there's not actually a stark contradiction in Hawking's calculation, because when Hawking does this calculation, it's in the low energy theory. And what we should really conclude from this is that the density matrix rho sub r of the radiation is thermal. That's Hawking's calculation, plus perturbative corrections, which you can calculate by loop diagrams, plus possibly non-perturbative corrections, which are of size e to the minus s, where s is the entropy of the black hole. The reason that we need to be careful with this approximation is that these e to the minus x corrections to the matrix elements of the operator rho sub r might be big enough to fix the entropy or to change the entropy at leading order. Because when you calculate the entropy, it's a trace of rho log rho. That trace is a sum over e to the s states. If you have a tiny correction of size e to the minus s, but you sum it over e to the s states, it could become something large. And so there isn't actually a contradiction between unitarity and Hawking's calculation. So why do people call it a paradox? Well, essentially because we didn't know any mechanism to fix this problem. There are no small corrections that can fix the problem. Anything coming perturbatively, like from loops, will not help. And there's no known mechanism for how the information can escape from inside the black hole to infinity. But what we're going to see in this talk is that we do now know how to calculate that entropy of the radiation, and it actually is compatible with the black hole being unitary. Here I have those statements here on this slide. I think this is what I just said. The new developments are that there are e to the minus s corrections to the gravitational path integral that produce large corrections to the entropy. when you include these effects, this calculation gives a small entropy consistent with unitary evaporation. The approach that I'll describe was inspired by ADS-CFT, but it doesn't rely on it. So actually, it came from ideas from string theory, but doesn't rely on string theory or ADS-CFT in the calculation that I'll describe. So let me now describe these new results, unless there are questions, if anyone wants me to pause here. I don't see anything, but please just interrupt if you have questions. So the starting point is this idea called islands, which was proposed in these papers in 2019. So what is an island? Well, this proposal is that the entropy of Hawking radiation should be calculated by a new formula, not by the usual formula, but by a new formula called the island formula. The way it works is the following. We're interested in calculating the entropy of the red region, the region R, where we've collected the radiation. To do that, we need to there's a new region called the island, which is the region inside the black hole that's entangled with the radiation. And then the radiation is calculated by this formula, which is called the quantum extremal entropy formula, or holographic entropy, or generalized gravitational entropy formula. And here's what it says. So it says that there are two contributions. There's a quarter of the area of the horizon. That's the first term. It's the usual entropy of a black hole. And then there's a contribution from the quantum fields that's called SQFT on this slide. So SQFT is the von Neumann entropy of the quantum fields in the region island union radiation. So you take the density matrix of the combined region, the blue and the red, you find the entropy of the quantum fields on that combined region, and that gives you SQFT. We're going to find later that this comes from what I call Z quantum, the loop corrections to the gravitational path integral. Once you have those, the island itself is determined dynamically by then extremizing this formula over the choice of the island region I. So this is a formula just for the entropy of the radiation. Now at late times, after the black hole has been evaporating for a long time, when you do this calculation, you find that the island is approximately the full black hole interior. Therefore, the Hawking radiation does not contribute to the second term, because this is the fine-grained entropy of the region R together with the island, which is entangled with R. Now, if you only see the outside Hawking particle, it has entropy, fine-grained entropy. But if you can see both the outside particle and its inside partner, now you have a pure state, and therefore it does not contribute to the entropy. Therefore, the second term doesn't contribute. The island formula tells you that the entropy of the radiation is just 1/4 of the horizon, and this goes to 0 as the black hole evaporates. That's what we need for unitary. So if the island formula is correct, then the entropy is behaving the way it should be for a unitary quantum system. This edge of the island is called a quantum extremal surface, and another relevant concept here is the scrambling time, which is how long it takes something to fall into the island before you can see it in the island. I've described this as a formula for the entropy, but it also has an interesting interpretation, something called entanglement wedge reconstruction that comes from the ADS-CFT correspondence. The idea is that the island is actually encoded. The island, this region that appears inside the black hole, the island region, is actually encoded in the radiation in a sense that's similar to holographic duality. In other words, operators in the island, like some field operator 5x, can be written as operators in the radiation in principle. although the actual way of doing that writing can be very difficult. This map from operators in the island to operators in the radiation is a very complicated one that connects to the subject of quantum error correcting codes and is a subject of a lot of study recently in ADS CFT. What I want to do next is so this island formula was proposed based on similar things that had happened in ADS CFT, but now what I want to do is to understand how to derive it from the gravitational path integral. This will involve a new kind of solution of the Einstein equation called replica wormholes. And the goal here is to derive the island formula directly from this Euclidean gravitational path integral that we discussed in part 1. We're going to use the replica method. So the replica method is a sort of a technical trick for calculating von Neumann entropies. The von Neumann entropy that we're interested in is S of rho is equal to minus trace of rho log rho. That log is tricky. Okay, so it's hard to calculate a log of an operator. So we're going to simplify this by trading the log for a power. So instead of calculating trace of rho log rho, we're going to calculate trace of rho to the n. If you can do this for all n, and if you can do an analytic continuation in n, then you can now take n near 1. And when you take n near 1, now you have trace of rho to the 1 plus epsilon, let's say. But the trace of rho to the 1 plus epsilon is the same, or if you then expand that in epsilon, then the leading term is trace of rho log rho. Okay, so this replica method is a trick to calculate logs of operators where you replace the log by something easier, which is this power. So that makes things easier, but what you then have to do is you have to understand how to do it an analytic continuation, because we're going to do this calculation at integer n, and then we need to do an analytic continuation to non-integer n. If we can do that, then we can extract the von Neumann entropy as S equals minus Z prime at n equals 1. The basic idea, I'm going to describe this better on the next few slides, but the basic idea is that when we calculate in the replica method, we need to consider contributions to the path integral that calculate the density matrix in the radiation region R. But when we have the replica method, there are different kinds of contributions. And in fact, there are contributions to the path integral in the replica method where the different replicas, which started out as independent physical systems, that these different replicas can actually have connections between them when you solve the Einstein equations. So there will be solutions to the Einstein equations that contribute to the path integral that connect the different replicas through the interior. And those connections between the replicas will be responsible for the island inside the black hole that calculates the entropy in the island rule. So these solutions that I'll talk about are complex geometries that we can construct by explicit solution of the equations of motion for gravity plus matter in certain simple cases. In the replica limit, which is this limit n to 1, these saddles, the wormholes disappear because now there's just one copy of the system, but they leave an imprint on certain calculations, including the calculation of the von Neumann entropy. So let's do the calculation. We want to calculate the replica partition function, Zn as trace rho to the n. Recall the basic formula for the path integral. It tells you transition amplitude. So this diagram on the slide is now the same thing I was drawing in part 1, that the Euclidean path integral calculates transition amplitudes between different states. Let's start with the easiest case, which actually is the same as part 1, where we set n to 1. If we set n to 1, then we're just calculating the thermal partition function, trace of rho. So here's a picture. This is exactly the picture that we drew at the end, that I drew by hand at the end of part 1. Rho sub r is the density matrix of the radiation region. So what we need to do is we need to do the path integral with the thermal boundary condition and a cut on the region R. And then in the semi-classical approximation, the solution that dominates the path integral will be the Euclidean black hole. So this is exactly that formula that I said we need to remember. The only difference here is that we're taking the trace, and when we take the trace, that just glues the region R back to itself and eliminates any dependence on that region. So this part here is the asymptotic part. That's the part where we impose the boundary condition. And then when we do the path integral, the semi-classical solution is the one that fills in with the black hole solution. Okay, that was just warm up. That's what we did before. But now I'm going to talk about the replicas. So now we're going to calculate the trace of rho sub r squared. Well, we need to follow the usual rules. Okay, so trace of rho sub r squared is rho sub r times rho sub r as operators. Okay, so how do we multiply two operators together? We take two copies of the operator. So the two copies of the operator are the bottom, or the top and bottom pictures that I've drawn here. These are two copies of the operator rho sub r. And then in order to multiply the operators, I've inserted a complete set of states, I, labeled I, and now we're going to sum over the states I. We're also taking a trace, which inserts another set of states, J, and we sum over J. Just as before, the effect of doing these sums over states is to glue the two manifolds together. And so now we're talking about a manifold that's glued together on the green line. It started out as two copies, but we take those two copies and we glue them together along region R. So we glue them together along the green line and along the blue line. And then we do the path integral with that crazy boundary condition near infinity. When we do the path integral, we need to find solutions of the semi-classical equations that have these boundary conditions. There's one obvious one, which is you just take two copies of the Euclidean black hole. This is a solution of the Einstein equations. It has the right boundary conditions. It's been glued together along the cut. And if you use this to calculate your path integral, you'll get Hawking's answer for the density matrix of the radiation. You'll find that it's in a mixed state. And if you apply this and go through the replica method and everything, you'll get back Hawking's calculation of the von Neumann entropy of the radiation. But there's another term, and that other term is the replica wormhole, and this is what's responsible for the sudden transition in the Page curve. So what is this other term? It's another contribution to the path integral where the two replicas are connected by a bridge. So it's a higher topology contribution to the Euclidean path integral. But the important thing here is that it satisfies the same exact boundary conditions as the first term. So again, when we do gravity, we're not allowed to say what the manifold is. We're only allowed to say what is the boundary condition. So we've imposed a boundary condition, and then we have to sum over all the saddles that satisfy that boundary condition. So there could be a contribution that has the topology of this wormhole solution. And it turns out there, in fact, is a solution. You can solve the equations of motion and find that there really is a solution with this topology. Therefore, when you calculate the replica partition function trace of rho r squared, there are two terms, at least, e to the minus the action of the first form of the first solution plus e to the minus the action of the second solution. And in each case, you have to also include the quantum effects of the matter fields. That first term, the Hawking type term, this is the term that we said the entropy is getting bigger and bigger. When you translate that back into a statement about the replica partition function, it means that the replica partition function is getting smaller and smaller. It's getting exponentially small as a function of time. So that first term is getting suppressed with time. The second term, on the other hand, is getting larger with time. And it starts out smaller, but it grows with time, and eventually the two terms exchange dominance, and there's something like a first order transition between the two saddle points. So these replica wormholes are n-copy solutions of the gravitational equations of motion sourced by the quantum effects, the one-loop matter stress tensor on the replica manifold. I've described the case of n, but for the von Neumann entropy, we need to be able to analytically continue. We need to be able to do this calculation for all n and continue n to 1. This actually turns out to be doable. You can set up the right boundary conditions as a function of n, and you can solve the Einstein equations for n near 1 and use that to calculate the von Neumann entropy. What happens is that the mouth of the wormhole becomes the island as we take n to 1, and the path integral gives exactly the island formula for the von Neumann entropy. So if we go back and look at the page curve, let me remind you what's going on here. This is the entropy of the radiation as a function of time. The red curve going up, that's Hawking's calculation. That's a violation of unitarity because it doesn't go to 0 at late times. What Page told us is that the correct answer should be the dotted curve. It should go up and then come back down. And now we've done this calculation properly using the gravitational path integral. The answer at early times is when the Hawking saddle point dominates. This is that sort of boring contribution to trace of rho squared. But at late times, that term gets very tiny. The replica wormhole saddle dominates. The connected topology dominates in the gravitational path integral because it has a smaller action. And you jump onto the green curve. And in fact, once you include both of these saddle points, both of these topologies in the path integral calculation exactly agrees with the prediction of Page, who modeled the black hole as a random Hamiltonian. Not just qualitatively, but it really agrees exactly. This is a whole function worth of agreement as a function of time. This is a very striking match between this random Hamiltonian and these curves. On these drawings, I've drawn the curves as just simple straight lines. That's accurate for two-dimensional gravity. In higher dimensional gravity, these are some complicated functions of t, but still everything works exactly in higher dimensions. You get whole functions worth of agreement. Okay, so that was basically the calculation that I wanted to tell you about. We've used this gravitational path integral that we described in part 1 to understand some feature of the entropy of Hawking radiation. I'm going to wrap up with a few comments and sort of remarks about what the open questions are and what people have been thinking about since then. But let me pause here and see if there are questions about the calculation. Okay, so let me summarize, make some comments. So first of all, does this show that black hole evaporation is unitary? No, doesn't show this. It is evidence in this evidence for unitarity. I think there's a question.
Yes, again, why at Latam the wormholes entropy dominate?
The action is basically e to the minus entropy. The action of these wormhole solutions is roughly e to the minus entropy. So as the Hawking entropy gets very large, the sorry, by action I mean the contribution to trace of rho to the n. The contribution to the trace is like e to the minus entropy. So as these curves get very large, they contribute a e to the minus s to the replica partition function. So the contribution of the red curve is getting exponentially small at late times, whereas the contribution of the green curve, which is the replica wormholes, that's getting bigger and bigger as a function of time, and eventually they cross.
I didn't get. I mean, why this wormhole entropy increase? How to see this?
I'm
I understand.
not sure. So
I understand that. Yeah.
I guess you're asking about the details of the calculation, and
maybe some general idea. Maybe it's a general idea, because okay. I understand why the Hawking entropy increase. It sounds like reasonable that the black hole decrease and so on. But what about the other part?
Yeah, the reason is basically that when you create this when you put in the higher topology in the wormhole saddle, that higher topology costs you some action. And so the second term has a very large action at the beginning. There's a large cost in the action from putting that higher topology, but the cost of the higher topology is controlled by the area of the black hole, which is related to the width of this tube. And so what you actually find in the calculation is that the contribution of the second term is e to the minus area. As the black hole then evaporates, the area goes down. So e to the minus area goes up. So the cost of making the wormhole is e to the minus area. Maybe the short answer to your question is that the cost of making the wormhole is e to the minus area. So when the area goes down, the wormhole gets less suppressed. Are there other questions? So it doesn't show that it's unitary, but it's evidence for this. The reason I don't think it really shows that it's unitary is because we use this postulate about the Euclidean path integral in order to trace rho sub r. That postulate has not been proved except in certain cases, like or if you assume ADS CFT. So without really understanding that better, I don't think we can say that it's a proof that it's unitary. There are a couple other directions that people have been thinking about a lot the last couple of years. One is whether there are interesting applications to cosmology in the very early universe. So in the very early universe, there are a lot of similarities between black hole interiors and early universe cosmology. In fact, once you're inside a black hole, it basically is a cosmology, because the inside of a black hole is a time-dependent space-time with a singularity. It's like a crunching universe. It's like the time reverse of the Big Bang. It's a big crunch. And so you might think that some of the lessons that are learned from these contributions in the black hole interior might also be relevant to cosmology. At this point, there has not been there hasn't been, well, the answer is we don't know yet whether there is anything like that, but it's something that people are really interested in, and exploring whether these new approaches to gravitational path integrals and higher topologies might have something interesting to say, even for, well, both for the theoretical understanding of de Sitter spacetime in the early universe, or maybe even for some signatures that could appear in the cosmic microwave background. The other big thing that people have been thinking about related to this is the problem is actually new problems that you create once you start including higher topologies in the gravitational path integral. Once we start including higher topologies, as we needed to in order to get the entropy to work correctly, now you have to, presumably you have to include them in other situations as well. But it's been known for a long time that in other situations, wormholes sometimes cause problems with quantum mechanics. They seem to violate some of the basic properties of quantum mechanics and create what are called factorization problems or factorization paradoxes. Basically, the issue that you get is that when you have, in quantum mechanics, you should always be able to project onto a complete set of states. So what I've drawn here is, imagine that we have some amplitude that has a wormhole contribution. Well, you should be able to project onto a complete set of states at any time inside that, any time in the middle of that calculation. But when you include higher topologies, there are now these new types of states that can show up inside your complete set of states. And in some cases, that can spoil quantum mechanical consistency conditions. So that's led to a lot of effort in trying to understand higher topologies in other situations beyond this calculation of the entropy. In some cases, we have some better understanding of those higher topologies. In others, there are still some open puzzles, and people are working hard to understand what those higher topologies mean. Okay, this is my last couple comments. So the conclusion is that ordinary rules of the Euclidean path integral can be used to calculate the entropy of Hawking radiation. The result agrees with unitarity and quantitatively matches these earlier predictions of Page. But this result also highlights the remaining puzzles of how to interpret the gravitational path integral. And that's it. Thank you.